Hi, and welcome to our second lesson on vectors. Yesterday we looked at unit vectors, so we got used to seeing a vector written in unit vector notation. That is, we got used to seeing this: some distance in the horizontal direction and some in the vertical direction, where I and j are the unit vectors that indicate each of those directions. Today what we'd like to say is that any vector can be turned into a unit vector by simply dividing by the magnitude. If you think about that, dividing through by the magnitude here will give you some fractional value in the I direction and some fractional value in the j direction. To find that unit vector again, what you do is divide the horizontal and vertical components by the magnitude of the vector. And just to get us started, we're going to take a look at an example that asks us to do that. You're going to find the unit vector that's in the same direction as 4i minus 3j. So if you think about that, the things that we need to do, we got to know the magnitude of that vector. And the magnitude is the square root of its a term squared plus its b term squared. And many of us would have been here long ago. That's a magnitude of 5. So dividing through by 5, we'll get that unit vector, and I'm going to call it u. Unit vector will equal, well, we had 4i. We need to divide that by 5. We had minus 3j, and that gets divided by 5. And there's our unit vector, folks. It says that we should verify that this has magnitude 1. We can do that quickly because the magnitude of this unit vector is the square root of its components squared and added. So 4/5 squared plus negative 3/5 squared. And let's see, if we do the math there, 4 squared is 16 over 25, you square top and bottom. Negative 3/5 squared is 9 25ths, and together that is 25 25ths, or 1, and the square root of 1 is 1. So we verified that we got back to a unit vector, and we did that by dividing the vector in its component format by the magnitude of. Okay, let's move on to our next topic here. We want to talk today a little bit about the horizontal and vertical components of a vector, because often they are of interest to us. So this vector, ai plus bj, is shown there. The point out here, a and b, tells us that this value is a along the x-axis or horizontal axis, and this is b along the vertical axis. The magnitude of the vector corresponds to the hypotenuse in this right triangle. Well, let's apply a little trig here. The angle theta is here, but you know when we do trig with this, we talk about its reference angle, which would be that one that we just put the dot in. So the sine of our dot angle, which is the sine of theta. I guess we don't need to use that terminology. We can just put a theta in there. The sine of theta is its opposite side, b, over its hypotenuse, which is the magnitude of that vector. It follows then that b would be the same thing as magnitude of the vector times the sine of theta. Okay, that must be true. We can do a similar thing with the cosine of theta there. It would be equal to a over the magnitude of the vector. It would follow then that a would equal the magnitude of the vector times the cosine of theta. So if you think about this, a and b, we have expressions that can be substituted in for them. So we can rewrite this vector definition in terms of the sine and cosine of the angle that it makes with the positive x-axis. So that vector, it could also be written this way. Magnitude of the vector times the cosine of theta, and that's in the I direction, the horizontal direction, plus magnitude of vector times the sine of theta times j, that's the vertical direction. Now you might be wondering why this would be an advantage to us, and I'll tell you, it can be used. Now we can talk about this vector algebraically, okay? The picture is great, and I understand where the picture comes from, but this gives me a way to talk about that vector algebraically, and that's going to be of use to us when we're solving problems. We'll begin our drawing with a little coordinate grid here, a horizontal and vertical axis. And the jet stream is blowing at 60 miles per hour. Again, that's the magnitude of this vector. Its direction is 45 degrees east of north. And that's interesting and necessary for us to know, because it tells us that if we consider the right angle here between north and east, that this angle inside is also 45. And I say inside because I'm going to make it a triangle. What we know is that the magnitude of that vector is 60, and we know the angle that it makes. So if we want to write the velocity of that jet stream as a vector in terms of I and j, we have just what we need, because we know theta is 45 and we know the magnitude is 60. So this vector is, according to our format up here, it's magnitude times the cosine of 45 is our theta in the I direction, plus its magnitude times the sine of 45 in the j direction. And I would just ask you to either remember, which I hope we all are by now, or look on your trig reference sheet. The cosine of 45 degrees is root 2 over 2. So we can do a little work here. That would be 60 times the square root of 2 over 2 in the I direction, plus 60 times the square root of 2 over 2 in the j direction. And simplifying would get us this for our vector. 2 goes into 60 30 times, so 30 root 2 in the I direction plus 30 root 2 in the j direction. And there's our vector in terms of the unit vectors I and j. Okay? 30 root 2 in the horizontal direction, 30 root 2 in the vertical direction. Good. All right, let's see if we can't use that. All right, let's look at a situation where we could use our algebraic definition of vector here, remembering that algebraically that vector is magnitude times cosine in the I direction plus magnitude times sine in the j direction, and I should have a theta in there. Let's read this problem. We have two forces, force 1 and force 2, whose magnitudes are 30 and 60 pounds respectively. So force 1 is 30 pounds and force 2 is 60. They're acting on an object. The direction, it says, of force 1 is 10 degrees east of north, and the direction of force 2 is 60 degrees east of north. We're to find the magnitude and the direction of the resultant force. So let's get a picture going here. Picture's worth 1,000 words. And here's our crosshairs, or our horizontal and vertical axes. Force 1, here's our object, 10 degrees east of north. So this angle is 10 degrees. The magnitude of that force is 30. And we have force 2, it says, at an angle of 60 degrees east of north. So that angle is wider, and the force is stronger in this one. Force is stronger in this one. 60 degrees there. Okay. So, and we've 10 degrees here. So I'm going to mark that 10 degree angle in red, I think. 10. Okay, let's see. And this one had a force of 60 pounds. Our job is to find, it says, the magnitude of the resultant force. And remember, the resultant force comes from adding. So we want to add together the vectors for force 1 and force 2. Let's find the vector written in this format for that force 1. Ladies and gentlemen, the magnitude we are given is 30, so we know that it's 30. The angle of this vector, and that's the angle that it makes in standard position. So not the 10 degrees that we've marked, but the rest of it is that vector in standard position. So that would be 80 degrees there. So we need that 30, the magnitude of it, times the cosine of 80, we've said, in the I direction. And we also have a magnitude of 30 times the sine of 80 in the J direction. Let's get the force 2 vector up there as well. The vector for force 2, well, it made an angle of 60 degrees east of north. That means that the rest of it, the part that we need, is 30 degrees. So the magnitude of that force 2 vector was 60. The angle that it makes with the horizontal axis is 30 degrees. So 60 cosine 30I and 60 sine 30J. Those are our two vectors written in algebraic format. Now let's do some work with these. We can turn this 30 times 80 cosine stuff into numbers. So I'm going to do that. In fact, I'm going to call my calculator up. Alright, you can see from my calculator that I've done the work for force 1, that vector. And 5.21 about is the value of 30 cosine 80. And 30 sine 80 is about 29.5. Done the same thing for force 2. In the I direction, it is 51.96 about. And in the J direction, it is 30 exactly. Now, we were asked to find the magnitude of the resultant, and the resultant comes from adding. So I'm going to add these two vectors together. F1 plus F2 is equal to, and let's do that work, 57.17I plus 59.5J. Now we have the resultant vector in algebraic terms. Our job is to find, it says, the magnitude and the direction. To find the magnitude, that's a matter of doing the Pythagorean theorem with these two numbers. So I'm going to do that in my calculator. We need the square root of 6,808.6589, and that's lots of digits of precision. We'll round back when we actually take the square root, and that magnitude is right around 82.5 pounds. Our forces were given in pounds, so our answer should be in pounds as well. Now, to find the direction, if you recall, you can find the direction of this vector by doing the tangent inverse of b divided by a, and that's exactly what we're going to do. Tangent inverse of 59.5 divided by 57.17. We're in degrees, and that direction is approximately 46.1 degrees. Now, this is the angle that resultant vector makes with the positive x-axis. And so we've answered both parts of our problem. We found the magnitude here. We found the direction here. So we have a force of 82.5 pounds that's operating in a direction of 46.1 degrees. Very good. The algebraic solution to that vector problem. If you've taken physics, you will have seen geometric solutions to problems like this, and we could have done that as well. It involves setting up a coordinate plane and using the law of cosines in a triangle. We could easily do that. We're going to show you a geometric solution to our next problem. And I would remind you as I'm talking that your book has worked out examples of these kinds of problems. So don't be afraid to look in the book if you want to see other examples. We're going to do a geometric solution to this problem. It says that an airplane is flying due west at a velocity of 100 meters per second. I am going to start my picture with a north-south and east-west axis because I think that's important. The airplane, it says, is flying due west, so it's going in this direction at 100 meters per second. At the same time, the wind is blowing out of the south. So this is the direction of our plane. The wind is blowing out of the south at 5 meters per second. So this is not drawn to scale, but the wind is having this effect, blowing it from the south at 5 meters per second. It says that we should find the magnitude and the direction of the plane's resultant velocity. Well, if you recall from our discussion of vectors, when we have them drawn tip to tail like this, the resultant is the vector that goes from the origin, where you started, to the tail of the second vector. So we're looking to find this value, that's our magnitude, and we're looking to find that angle, okay, little tiny angle right in there. Alright, so, you know, since this was west and south, we have a 90-degree angle right there, which makes this problem way easier to solve geometrically. This is a Pythagorean theorem thing. The magnitude of that vector will be the length of the resultant. And let's see, that would be the square root of 5 squared plus 100 squared. And that would be, let's see, 100 squared is 10,000, so 10025. We need the square root of that. Right about, see, the wind's giving it a little advantage, 100.1 meters per second. To find the direction of that velocity, well, that's a tangent inverse of this thing. I would remind you folks that this is going in the westerly direction, so really that's negative. The angle that we need will be the tangent inverse of opposite 5 over adjacent negative 100. And it says that that angle is about negative 2.86 degrees. I would remind you that when you use tangent inverse, you get things that are in either first or fourth quadrant. Our angle is in the second quadrant. So to find the direction of ours, we got to add 180 degrees to that, just because we know we need to get not in the fourth but in the second quadrant. So let's add 180 degrees to that. And our angle is 177.1 degrees about from the positive x-axis, so in standard position. Our magnitude, our direction. Very good. We've solved problems with vectors both geometrically and algebraically. This one turned out to be nice geometrically because it involved a Pythagorean theorem calculation. However, had we, I'm going to go back here just for 1 second, had we solved this problem with a geometric solution, we would have ended up having to use the law of cosines to find a value for our resultant. I am going to ask you to get out there now and try that U-try as quickly as you can, and we'll see you in school tomorrow.